Thank you very much. Good afternoon to everybody. First, I would like to thank the organizer for this very nice, kind invitation. I am enjoying the conference very much, and I will try to bring my own input by talking about gravitational wave source modeling using post-Newtonian approaches to show you where we are and what are the challenges we have to face. First, let me describe a little bit what is the post-Newtonian approximation. Then I will discuss the status of the gravitational wave generation formalism before talking about the near-zone dynamics. And I will end with the challenges if I have time, but for those who are here tomorrow, I will say more tomorrow in an informal talk. The post-Newtonian approximation is a versatile perturbation scheme used in general relativity to model systems with small velocities with respect to the speed of light. This means that the size of the system must be small with respect to the wavelength, and therefore we have to restrict ourselves for the validity domain to a domain which is much smaller than the wavelength. Here is the wavelength, and here is the source, for instance. This is our near-zone domain. And only in this domain, the post-Newtonian approximation will be valid. We can replace the field h mu nu by h bar mu nu, which is the post-Newtonian version of it. In the exterior zone, outside the system, you can actually use the multipole expansion together with the post-Minkowskian approximation. So in that case, the post-Minkowskian solution will diverge inside the system, whereas the post-Newtonian expansion is perfectly well-defined inside the system, but diverges in the exterior zone. We will be interested mainly in compact binaries. For those systems, the small parameters will be the relative velocity squared divided by c squared, or equivalently, because they are bound systems, in our case, the Newtonian potential divided by c squared. Because we will assume that the objects are compact, the separation ratio, I mean the radius divided by the separation, will also be equal to the small parameter. We have two bodies, y1, y2, with masses m1, m2, and velocities v1, v2. So in our counting, the leading order quadrupolar flux will be referred to as the Newtonian order. It's a bit strange because we know it is proportional to 1 over C5, but this is the terminology we use. As everybody knows, because of the balance equations for E and J, due to gravitational emission, gravitational wave emission, the eccentricity of the binary system goes to 0 for isolated binaries, and the energy, and therefore the separation decreases at a rate corresponding precisely to the second and half post-Newtonian order, epsilon to the fifth half power. We have a modified Kepler law, so this is the first post-Newtonian correction of the Kepler law, for instance. The relation between the energy and the frequency, which is represented through x omega to the 2/3 power. So this relation is also affected by post-Newtonian corrections. Notice that we will focus on circular orbits for the observable results. And in that case, those relations for the energy and the flux, so those expressions are gauge invariant in terms of the frequency or of the variable x. The convergence of the post-Newtonian series is not very good near the innermost stable circular orbit, defined a bit formally in that case. It becomes also very slow when the mass ratio is far from 1. Things improve for comparable masses. we may cure that using the effective one-body approach introduced by Bonanno and Damour in 1999. So the idea is that in the center of mass frame, we can use only the position, the relative position, and one of the momenta to describe the dynamics. So it's effectively as having one body, but then the dynamics in an appropriate coordinate system in the phase space is described by some very convenient Hamiltonian. It is convenient in the sense that it is a simple function of an effective Hamiltonian corresponding to an effective metric in the sense that this is the Hamiltonian of a test particle moving in this metric. And this metric is nothing but a deformed Schwarzschild metric, as you can see. The usual on-shell mass condition that p square is equal to the reduced mass square or minus it has to be a little bit modified, but essentially this is the scheme. And this is, of course, supplemented by a lot of things, but I have no time to go to details. To improve the convergence, you can also resort to appropriate approximants, like Padé approximants, or even other approximants, if you like Chebyshev polynomials, or whatever. And you may also find useful to factorize asymptotic behaviors which are known from the post-Newtonian result I will present. So all those techniques are used to design actual waveforms in the EOB scheme, effective one body. But I will not talk about this anymore in the rest of the talk. There are several versions of the post-Newtonian formalism. One version is the post-Newtonian iteration scheme in harmonic coordinates with a French side and an American side. The French side uses a point particle representation supplemented by dimensional regularization with asymptotic matching. And the Americans prefer perfect fluids. Another interesting method is the Einstein-Hilfeld-Hofmann method, where we can avoid the annoying strong field region using mathematical tricks. But this is very difficult to implement. Recently, a lot of people have been working on effective field theory approach in harmonic coordinates, EFT. Very powerful approach for the near zone problem. Perhaps the most powerful is the ADM Hamiltonian approach introduced in the 80s by Gerhard Schäfer. The gravitational field will be described by the deviation of the Gothic metric from the flat metric. We are in harmonic coordinates. We have this Lorentz-like gauge condition. Then the ancient equations are like wave equations with an effective source tau mu nu. This source is made of the stress energy tensor plus nonlinear corrections. The idea is then to decompose H into post-Newtonian contributions at various order M. And if we assume that the previous orders are known, we can obtain the solution at order M in the following way. We apply the retarded integral on the source tau mu nu. We expand it formally as if we were allowed to do that mathematically. But to correct this mathematical error, so to say, we have to add the correct homogeneous solution to the equation, which is given by this term here, where the R here are multi-index quantities. So L here represents L indices I, and they depend, those quantities, they are explicit functionals, a bit complicated, depending on the multiple moment outside the system. So it's not the post-Newtonian expansion. So you see it's interesting, the post-Newtonian order M will depend on non-post-Newtonian inputs here. So the post-Minkowskian expansion. And then we go to the next order and we iterate. Now, let's talk about the generation formalism, and let's see where we are now. So I will focus, therefore, in the exterior zone, and I will consider those approximations here. The field point will be called X. R is the distance to the origin. We are at time t, and the retarded time will play an important role, and you'll see why immediately. It is because, actually, the Einstein equations in the vacuum becomes those simple equations in harmonic gauge, and at linear order, this is even 0. And we know the most general solution, which has this form, with the same multi-index notation as before. Here we put only retarded terms and not advanced terms, because we assume no incoming wave condition. And therefore, after a small rearrangement of this solution and imposing the fact that we have this gauge condition, we find that h mu is a functional of some source moments and gauge moments. Two source moments are the mass type and current type moments, and they can be computed using asymptotic matching techniques as explicit integrals over the source. So for instance, this is made with the effective stress energy tensor. Here, this is a kernel depending on the position appearing in the integration here. It's a space integration. This means symmetric trace-free over the indices L. And there are corrections to that formula. I didn't put them. They are not so important to understand what's going on here. Now, in the post-Minkowskian iteration, we start from the solution I just showed you, which was the case g to the power 1, so when n is equal to 1. But we add more powers of g, like here. And if we assume that the solution is known at the previous order, you can compute the next order by using some box -1 operator. Actually, box -1 is not a convergence integral, because the retarded integral does not converge applied on multipolar sources. But you may cure this by using appropriate regularized retarded integrals. And they are still solution of the wave equation, so it's okay. However, you need to impose also the gauge condition, the fact that the divergence of h mu must be 0. But you can notice that if you add the correction to have the gauge condition satisfied, this correction must be a solution of the vacuum equation, box equation. And therefore, it's easy using now the fact that the divergence of h must be 0 to actually integrate the equation I am showing now and to get q, hence h mu nu at the order we want to compute. Finally, I need to introduce the concept of radiative multiple moments. So if I write the gravitational wave in terms of the position and time, well, there is a radial dependence in 1 over r plus 1 over r square corrections, which are negligible. The angular dependence is encoded here in n. N is the direction from the source to the observer. The observer is here in this direction. It's a unit vector. It depends on the angle theta and phi. So the angular dependence is really encoded there in the red n. This means a product of many n vectors, actually, n minus 2 of them. And here is the time dependence. Those coefficients are precisely the radiative multiple moments. So they parameterize our gravitational waves. Another way, which is completely equivalent to parameterize it, is to consider this complex combination and decompose it in terms of spin-weighted spherical harmonics. And we have ULM and VLM playing the same role as the U and V before. Now, we can compute the dynamics of the source using the post-Newtonian scheme, from which we know the effective stress energy tensor. we, by integration, deduce from that the source moments. And by applying the previous algorithm, we can compute h mu outside the system. And now we compare our result for h mu with the previous parameterization of the gravitational wave, from which we get the relation between the radiative moments and the source moments. It's useful to introduce also canonical moments. And in fact, instead of expressing UL, for instance, in terms directly of IL, JL, and so on, we will prefer to express them first in terms of ML, SL, and then ML, SL will be functionals of IL, JL, and so on. So those radiative moments, once we have computed them, we see that they decompose in the following way. So there will be an instantaneous part. This is made of terms which have this aspect. So they are derivatives of with respect to time of multiple moments evaluated at retarded time, and in fact, product of such terms appear, in fact, in the instantaneous part. Then there is the tail part. This is given by an integral depending weakly on the source past history, so before the retarded time. This effect is related to the scattering of the linear wave on the curvature of space-time. And there is another important effect, which is the memory effect here. And this one is also hereditary and depends strongly on the source past history. This is related to the fact that the gravitons fill the space-time and generate themselves gravitational waves, non-linear. Besides of the tail effect, there is a tail of tail, tail of tail of tail, and so on effects, which are just multi-scattering of the waves. Now, this is an example of a recent result. We have been able to compute the link between the radiative moment and the canonical moments up to 3.5 PN order. So it's not particularly interesting to contemplate, so I will go quite fast. But here you see that the radiative moment is just essentially the fourth derivative of the canonical moment, plus many corrections. Here I took the example of the hexadecapole. You can do the same quadrupole. But this was a new result. This is why I show it. Here, there is the tail of tail integral, which was new for the octupole here. It's a hereditary effect, as I said. You can see the multi-scattering of the wave twice, actually, on the mass of space-time. You see the wave is here, and there is a kernel which is logarithmic. Now, if I want to summarize the recent results about higher order amplitudes, I would say that we know the amplitude for circular orbits at 3 PN. And for eccentric orbits, actually, we have partial results at 3 PN also. So for the moment, we are a bit blocked because more results must supplement the case that has been published, corresponding to the instantaneous part of the waveform, where we forget about the tail and memory contribution. I think the pointer starts to become a bit weak. Okay. So here you can see also that some modes at 3.5 PN have been recently computed. So 3.5 PN, I remind you, this is 1 over C7. So 2,2, for instance, which is the dominant mode, but also 3,3 and 3,1. So the completion of this of those works is in progress. In particular, we are computing the mode 2,1, which is a difficult computation. Now let us go to the near-zone dynamic. 15 minutes, so I think I have time to say a few words. Thank you. Yeah, thank you very much. Here, let me tell you quickly the two main methods we use to derive the equations of motion. So the most powerful method is the FOKKER-Lagrangian method. So you take the Einstein-Hilbert action, or better, the Einstein action, and you add the matter contribution, of course. Then you replace inside this action the field variable by the solution of the Euler-Lagrange equation for the field. So this means, this REE means relaxed Einstein equation. This means that this is a solution of the field equation obtained from the original action. Then you obtain a reduced action, and this reduced action has a very important property. So if you had computed the equation of motion for the matter, and then replaced H by the solution of the Einstein equations, you would have found the same thing as when you derive the equations of motion for the matter using directly the effective action. So we don't need actually anymore to refer to the full action. We can, for the matter part, use only the effective action. There are some restrictions, so we should, for instance, use to invert the box operator, not the retarded inverse box operator, but the symmetric one. But this is a technical problem. I will not go to those details. Another method is to actually use an effective stress energy tensor and to derive the equations of motion from the conservation of this stress energy tensor. Once we have the equations of motion, we compute the conserved quantities, notably E and J, in the center of mass frame. We then compute the source moments and the radiative moments using what I explained in the previous slides, the first part of the talk. Hence, the polarization amplitudes, as for the phase, it is derived using a balance argument. In the case of circular orbit, the energy and F, the flux depend only on the frequency, orbital frequency omega. And so actually this equation, together with the definition of omega, is sufficient to integrate omega in terms as a function of t. Hence you can also derive the phase as a function of t. So yes, very quickly, the interesting point in using effective actions is that they are particularly useful to implement extended body effects, even though we work with point particles. So we have genuine point particles from the mathematical point of view, but physically we modify the action to take into account the finite size effects. So for instance, the particle here is at position y mu with velocity u mu, and it will be useful to introduce a fixed tetrad. This is chosen, for instance, using the gauge condition for the coordinate system where you are. Well, there are several ways to fix this. And then there is a another tetrad moving along the world line associated with the body. And actually, there is a Lorentz matrix linking the two tetrads. So here you can see actually the relation between them. And so it is quite clear that this is the second tetrad which is relevant to define the rotation vector and therefore the spin. And the Lagrangian we will consider will depend on the velocity, the rotation vector, G mu mu, and also the Riemann tensor and the derivatives of the Riemann tensor in the vacuum. So the Weil tensor, if you prefer. Now, we can, from this very general action, derive a stress energy tensor. So we use this notation for the world line density, which is the generalization for point particles of the usual rho of X for fluid. We introduce an effective linear momentum, an effective spin, defined in this way, and the so-called Dixon momenta, so Dixon quadrupole, octupole. And it turns out that you can express the the stress energy tensor in this way. So you see there is a term proportional to the Dirac distribution, another, the derivative of the Dirac, the second derivative, the third derivative. Here you have the monopole, here the dipole with the spin, here the quadrupole, here the octupole. But those quadrupole octupoles, they interfere also with the monopolar part, and the dipole part of the stress energy tensor. Okay. So now, we alternatively can describe in a more specific way the action of the Lagrangian. So for instance, this is the action describing tidal effects for bodies in quasi-equilibrium, so in the adiabatic case. So the bodies are supposed to stay at equilibrium in their co-rotating frame all the time, which is an approximation, of course. And you see here that we have some scalar invariants. They are the only invariants we can build if we have one structureless body, and the only structure we expect is due to the other body. And they are built using, of course, the Riemann tensor invariants, so the magnetic and electric invariants, and their derivatives. Those allow us to define mass-like tidal moments and current-like tidal moments. And the coefficients here in front of this are related to the love numbers. They are the relativistic definition of the love numbers. Here, for instance, you can see that the effect is proportional to some power of the radius of the body. This is for each body that we have this action. And for the quadrupole dominant contribution, L equal 2, this is R to the power 5. And remember that R is like 1 over C squared for a compact object. So this is a 1 over C10 effect, a 5pn effect. It's a very small effect, this tidal effect. Also, it's interesting to investigate, as we saw yesterday. Now, similarly, we can more specifically model the action. Here, this is the Lagrangian rather than the action, actually, for spinning objects, neglecting the tidal contributions for the other body, assuming that everything comes from the body we are considering. And so we construct the most general scalars using, again, the Riemann invariants or their derivative, an alternative way to write the tidal moments, actually, and the spins. You can construct them in two ways. By a parity argument, when it's electric, you must have an even number, and when it's magnetic, an odd number of spins. I want to emphasize the fact that this Lagrangian is effective. So, for instance, there is no reason why the mass is related to p squared using the usual formula. S mu is an effective spin, p mu an effective linear momentum, and so on. Finally, by identifying the stress energy tensor derived from those types of actions or Lagrangians, and comparing with the previous skeleton T mu nu, we can actually compute explicitly the Dixon moments for those models. Yeah. So now, if I consider the spinning case, for instance, which is particularly interesting, two spinning bodies separating by R12, they can precess about the rotation vector omega 2, precession vector omega 2. The orbital plane precesses. There is a misalignment between the total angular momentum and the orbital angular momentum. And here the resonant effects are ignored. The absorption effects due to black holes, if we have black holes, are ignored. And the motion will be regarded as quasi-circular. M will be the total mass, mu the symmetric mass ratio, and S and sigma are made of the two spins, so they are symmetric and antisymmetric variables. So the phase has this structure here. So maybe I will a bit skip this just to show you the spin orbit contribution. So in color, those are the recently added terms. in the phase. So the most recent is at, so for the spin orbit, is at 3.5 pn, and even 4 pn if you take into account the tail effects. This is 3 pn for the spin square effects. The kappa plus and minus are related to the deformability parameters of the Lagrangian I showed before for spinning bodies. And the kappa plus, for instance, is kappa 1 plus kappa 2. And kappa 1 is 1 for black holes. And for neutron stars, those kappa are of the order of 3, between 4 and 8, I think. So this, even this cubic contribution to the phase is known with similar deformability parameters here. So when I say deformability, I mean that the object gets an octupole because of the spin. So it's an induced octupole, and the same for the quadrupole. The octupole corresponds to spin cube effect, quadrupole spin square effect. And finally, this is the phase with the tidal contribution here. This was obtained by Vines, Flanagan, and Hinderer, and improved by Damour, Nagar, and Villain, but still we don't know even the 2 pn contribution in the phase. This is the love number for the quadrupole. This is the ratio between mass 1 and m, this x1 here. And one must add the contribution for the second body. Okay, so maybe I have only 3 minutes left. So maybe I will skip this. This is the statue about the spin, so you can ask me if you like. And quickly, I want to discuss the challenges. So now we are computing the non-spinning equations of motion at the 4 pn level. And so we start from the Einstein action supplemented by the matter part here, the standard one. I mean, absolutely standard, except that we add a gauge fixing term. Otherwise, this operator here, when we compute the equations of motion using the Lagrange equations, Euler Lagrange equations, would not be invertible. So we need to have this gauge fixing term, which doesn't change the physics. This modifies the nonlinear part of the source. We don't impose by hand at all the harmonicity condition. We are really off-shell. Now we write the Lagrangian by integrated by part under this form. So this will allow us to build the propagator, if you like. And now we use a very crucial lemma saying that we can decompose the Lagrangian into a part depending on the post-Newtonian expansion and a part depending on the multipole expansion. This part actually is very tiny, 5.5 pn order. So only the near zone part will contribute at 4 pn. We need to perform this splitting to introduce a regularization procedure with a cutoff R0. Now there is a very interesting feature about FOKKER Lagrangian. I have no time to explain it, but basically because delta S over delta H mu u is 0 for exact solutions of the field equations, it turns out that if you want to have a reminder when computing approximate Lagrangians or actions equal to an order 2n, you need to have H, the metric itself, only at order n, so half of the required order. So the H mu nu homogeneous solution, remember it had this form, and we inject this in the previous action, and this gives an effect which is non-local in time, but contains a conservative part. This is the so-called tail effect. And this tail effect, for instance, reads this for the 4 pn action we considered. Notice here that we have to introduce some other regularization procedure. Actually, this is quite equivalent to the previous one, except here, a priori, we have a different cutoff, but we can show that this cutoff relates to the previous one by only a constant factor, and we introduce this alpha here. It will be very important. We cannot determine alpha for the moment. This Ij is the quadrupole of the body. This means the third derivative. And so you see that the tail integral is non-local, the tail action is non-local in time. More precisely, the Lagrangian will be only one integration instead of two, is non-local in time. So this is very interesting. So we have used this action and applied the three-step procedure to compute the final effective action. So we have integrated the Lagrangian density explicitly using dimensional regularization for the UV divergences. We have reduced the Lagrangian, eliminating the higher order derivatives of the matter variables. And the result does not depend on the cutoff R0 anymore. It is manifestly Poincare invariant. It has most of the, the properties we can easily check. It possesses all. Then, unfortunately, alpha cannot be, does not disappear from the final result, but it can be computed using comparison with self-force results. After doing this and fixing the value of alpha, we found that our result does not agree with the recently computed Hamiltonian at 4 p.m. by Damour, Jaranowski, and Schaeffer. So we are working now on fixing the problem. The difference is not so large, actually. This is not so bad. We agree at least for the energy. So I show for completeness the energy for circular orbits at 4 p.m. So we agree on those coefficients, and in particular this one, which is non-trivial. And okay, so we plan to compute the phase at 4 p.m. And so it will be a long way. We need to compute the multiple moments, and notably the quadrupole and the link between the radiative quadrupole and the other moments. But it is in progress with PhD student Tanguy Marchand at IEP, working on that. And I will end, this is my last slide, so by briefly mentioning other challenges. So we would need to complete the computation of H plus and H cross at 3.5 p.m., go beyond quasi-equilibrium configurations and beyond Newtonian order, because some work is already done in that direction, but at Newtonian order. And for spinning binaries, it would be nice to obtain the 3 p.m., even 3.5 p.m., I think, amplitudes, and to compute all 4 p.m. spin contribution to the phase, so go beyond what we have. We have only the spin orbit contribution at 4 p.m. for the moment. Take absorption effects into account if we have black holes, and investigate the dynamics beyond quasi-circular motion with spin and eccentricity. Okay, sorry for being long, but I stop here.
Okay, thanks, Guillaume. So are there questions for Guillaume? Yes, Ajit.
Guillaume, what is the new work on and computing the tidal effect? It's a higher order computation or something fundamentally new?
No, it will not be new. Just that actually, I don't know. I'm not sure if it is very, very important to compute them. If people need it, perhaps yes. I have to discuss with people to know that. But actually, what they do is that they use partial results, because very often they use the dynamics, including tidal effects at 2 p.m. Because for the dynamics, they are known at 2 p.m. But for the phase and for the rest, they are known at less than 2 p.m. So it's a bit inconsistent. So probably it doesn't play any big role, especially for the current detectors. It is not so important, perhaps. But at least, for instance, for comparison with numerical simulations or for finer investigations, probably it could be interesting. I don't know yet, but it's just a thing I said one day I would do, so perhaps I will do it or not, I'm not sure.
Okay, are there any other questions? If not, let's thank Guillaume. Thank you, Guillaume.